Hello friends, welcome back to my YouTube channel Doctor's Corner. In the today's lecture, we'll discuss one of the very important topic in general physiology, resting membrane potential. Okay, we'll be discussing the definition of the resting membrane potential and the genesis of the resting membrane potential in the today's video. Okay, so before going to the definition of the resting membrane potential, I'll give some background so that the concept will be more clear to you people. Now consider a cell. Okay, a cell. Human body has trillions of cells. So consider, okay, now more specifically a neuron. Okay, a neuron. So the fluid which is present inside the cell, it is known as intracellular fluid or ICF, and the fluid which is present outside the cell, it is known as extracellular fluid or simply ECF. Okay, now you people know that inside the cell there will be many ions present. Okay, the positive ions are known as cations. Okay, they will be positively charged, they are positive ions, and negative ions are known as anions. Negative ions are known as anions, they will be negatively charged. Okay, so example of a cation or a anion, so cation, that is the positively charged, are, for example, sodium. Okay, sodium and potassium, these are positively charged ions. Okay, calcium. Okay, calcium will be 2 plus, valency is 2 plus. Okay, similarly negatively charged ions like chloride, phosphates. Okay, then we have organic also negatively charged inside the cell, proteins. Okay, similarly in the extracellular fluid also we have the similar positive and negative ions, that is the cations and anions, sodium, potassium, calcium, chloride, so and so. Okay, but this proteins and phosphates, okay, these are more, they are present in the intracellular fluid. Now this ionic concentration, sodium ions or potassium ions and calcium ions, they are not equal on either side of this cell membrane. Consider this is most important as a cell membrane. Okay, neuron cell. So the charges which are present are not equal in concentration. What I mean to say here is, for example, potassium ion. Okay, if we consider this a potassium ion inside the cell and outside the cell, the concentration of the potassium ion inside the cell is around roughly 140 to 150 millimoles per liter. Okay, roughly you take it as 150 millimoles per liter, and outside this it is just 3.5 to 5 millimoles per liter. Okay, such a difference. Okay, inside the cell the concentration up to 150 and outside just 3.5 to 5 millimole. Similarly, if we consider one more cation, sodium, the concentration on this sodium outside the cell, that is extracellular fluid, it will be around 150 millimoles per liter, and inside it will be just around 15 millimoles. Okay, 10 times lesser, 15 millimoles per liter. So the concentration, it is more outside as compared to the inside. Okay, so similarly chloride also is more outside as compared to the inside. So the ions are not distributed equally in the intracellular fluid and extracellular fluid, that is the concentration varies. Now why this concentration varies, what is the reason, that we are going to discuss in the coming section of resting membrane potential, and meanwhile we'll define what is resting membrane potential and why it is so. Okay, so before that, just have this background. Potassium is the main intracellular cation and sodium is the main extracellular cation, that is which is present more outside the cell, sodium outside and more potassium inside the cell. Okay, now let us try to define what is resting membrane potential here. So if we consider this as a cell, okay, more specifically take it as a neuronal cell or a neuron, okay, nerve cell, a neuron. So if we place a voltage recording device, that is voltmeter or a cathode ray oscilloscope, basically it is a voltmeter which will record the voltage difference, okay, in between the electrodes. So if we keep one electrode on the cell membrane, okay, on the cell membrane, and another electrode also on the cell membrane, now the voltage deflection will be zero. There will be no deflection of the voltage if we keep both electrodes on this cell membrane. But if we keep one electrode inside the cell with the help of a micropipette, okay, micropipette having some electrolyte solution. So if we keep one electrode inside the cell inserted and one electrode outside the cell, now there will be certain deflection in this voltmeter or the cathode ray oscilloscope. So that deflection is recorded, and for a neurons, in human neurons, a small size neurons, medium size neurons, it will be around -70 millivolt. Okay, if we keep both the electrodes outside the cell membrane, it will be 0, but if we insert one electrode inside and one is still outside on the surface of the cell membrane, then it will be -70 millivolt. Now what is this -70 millivolt? Resting membrane potential. So to define what is resting membrane potential, it is the potential difference across the cell membrane at the resting condition of a cell. It is known as resting membrane potential. Remember, all cells of our body will have the RMP or the resting membrane potential, all cells. This RMP or resting membrane potential is usually negative, and the value varies from -9 millivolt to -100 millivolt. Okay, different cells have a different resting membrane potential. In our example of a neuron or a nerve cell, it is -70 millivolt. Cardiac muscle will have around -90 millivolt, and smooth muscle cells will have -55 millivolts. Skeletal muscles are also having around -85 to -90 millivolt. RBC will have around -7 millivolt. So different cells will have a different resting membrane potential, but all cells, remember, will have resting membrane potential. There is one more term, action potential, which we are going to discuss in the coming lectures or the coming videos. So when the cell is stimulated, the series of electrical changes or the potential differences, what we are going to see in this cell when the cell is stimulated, that is known as action potential. Okay, the action potential is not seen in all the cells of our body. It is seen only in the excitable tissues like neuron or muscles include smooth muscles, cardiac muscles, and skeletal muscles. Okay, so different cells will have a different resting membrane potential. I hope the definition of resting membrane potential is clear by this time. That is, what is resting membrane potential? Resting membrane potential is the potential difference across the cell membrane at the resting condition of a cell. It is known as simply resting membrane potential. Now, why it is so? Why it is negative, and why this value of -70 so and so in a neuron cell? So we'll discuss how it is developed, how this potential difference is developed inside and outside of the cell. So we are discussing under the heading of genesis of resting membrane potential. Okay, how this resting membrane potential is generated. It can be a 10 marks or a 5 marks theory question, okay, in the first year MBBS subject physiology. So please give your kind concentration here. We will be using some mathematical or physics formulae to describe the genesis of the resting membrane potential. So we'll discuss one by one. So firstly, sodium-potassium pump, sodium-potassium ATPase pump, to be more specific. Okay, so as you people know, on the surface of these cells, there is on the surface of the cell membrane, there is a sodium-potassium ATPase pump. Okay, hope you have studied the sodium-potassium ATPase pump under the section of transport across cell membrane. That is the active transport and primary active transport. Primary active transport, example, sodium-potassium pump. So what actually this pump do is, it will transfer 3 sodium ions from inside to outside the cell. Okay, 3 sodium ions will come from inside to outside the cell, and simultaneously what will happen, two potassium ions from outside to inside. Okay, so when it transports 3 sodium ions from inside to outside simultaneously with the same energy, this one, 2 potassium ions are transmitted inside the cell. Okay, so out of all the cellular energy used, around this pumps use around 25% of the cellular energy. Okay, it will be continuously working. It will be continuously making 3 sodium outside and 2 potassium inside. Okay, now with this concept, you can see because of this pump, more amount of this sodium will be coming where? So it will be more amount of this sodium will be in the extracellular fluid. Okay, one point to describe that why sodium is more outside the cell as compared to the inside, and inside this there will be more amount of the potassium, okay, as compared to the sodium, okay, because it is pouring 3 sodium outside and 2 potassium inside. So more importantly, the more important intracellular cation will be now potassium and extracellular will be sodium. Now simultaneously it is generating negativity inside. Why? Because more positive ion is going outside and less positive, that is 3 positive charges are going outside and only 2 positive charges are coming inside. Okay, so there is a net loss of 1 cation. Okay, that is 1 positive charge is net loss. So there will be more negativity inside this cell. Okay, so there will be more negativity inside the cell as compared to the outside. This is the one of the reason to explain this resting membrane potential, why it is negative. So one of the reason, but it is not the main factor. Remember, sodium potassium pump, though it will generate a negativity inside the cell, but it has a very minute role. So if I consider, if like minus 70 millivolt of a neuron resting membrane potential, so this out of that minus 70, this sodium potassium pumps will just contribute to around minus 4 to minus 5 millivolt. Okay, so remember, most of the students think that this resting membrane potential is mainly due to sodium potassium pump. No, it has a minor role for genesis of the resting membrane potential, but it is not the main reason. Okay, it will just generate a negativity of around minus 4 millivolt. So this resting membrane potential, as I already described in the definition, you know, there are so many cations and anions inside the cell. So all this cation and anion, there will be so many cations and so many anion, that is positive charge and negative charge. So for one positive charge there will be one negative charge and they get neutralized. Okay, for one positive charge there will be one negative charge. There will be so many positive and so many negative charge inside the cell as well as outside the cell, that is extracellular fluid. So many that positive charge will get neutralized, one positive charge will get neutralized with one more negative, but few extra cations or anions which are not neutralized by their opposite charge, they come and remain near the cell membrane. Okay, so here inside, when this all are saturated, few extra anions will be there, like proteins, or which are not, or even this chloride and all, proteins or phosphate. So this anions, negative charge comes around the cell membrane, and similarly outside of the cell also there will be, if extra charges will be coming near the cell membrane, and this resting membrane potential is because of this extra charges. So what does this minus 70 millivolt means? The interior of the cell is negative, with minus sign means it is negative with respect to exterior of the cell. And how much negative? It is minus 70. If it is minus 95, for example, minus 95 or minus 90 in cardiac muscle and all, so that means it is more negative. If it is minus 55 in smooth muscle, if that is, it is though negative but magnitude is less. Okay, the more minus means that is, it is more negative. Okay, less amount minus, it is less negative. So I hope the concept is clear. So mainly this resting membrane potential is due to these charges which are near the cell membrane. There will be so many positive and negative charges inside the cell membrane, but they get neutralized, and mainly this potential difference is because of these charges which are near the cell membrane. Okay, so the resting membrane potential is the potential difference across the cell membrane at the resting condition of the cell. So one factor is sodium potassium pump. Now second factor is selective permeability of the cell membrane. Selective permeability of the cell membrane. So you people know it very well. This cell membrane is a lipid bilayer semi-permeable membrane. Okay, so selective permeability of the cell membrane. So that means the cell membrane acts as a selectively permeable membrane, that is, it will allow only few substances to pass across the cell membrane, not the all. Now let us discuss what exactly it is related to our concept of resting membrane potential. So on the cell membrane, if you consider, there will be so many ion channels. Okay, these ion channels can be leaky ion channels, voltage gated ion channels, ligand gated ion channels. We are not going to discuss in detail about that. Simply a ion channel, this will be protein in nature or made up of this peptide units. Okay, so protein nature or leaky channels, okay, consider these as the potassium channels, okay. So ion channels which are made up of protein, that is the protein channels, so through which potassium can diffuses out or come inside, okay. Similarly, we have different ion channels for here consider this as the sodium ions, okay. This is for this one, and consider this as the sodium ion channels, okay, sodium ion channels through which sodium can either enter and go outside. Now forget about this sodium, now concentrate, there will be chloride channels, so many other ion channels, even voltage gated and all, we'll discuss in the coming sections. But right now concentrate on this potassium, okay. So this potassium, as you know, I have already described you, it is the main intracellular cation, that is the concentration, it is more, it is around 140 to 150 millivolt in millimoles per liter inside the cell. Outside it is just 3.5 to 5 millivolt. So where the concentration gradient, it is where the concentration of the potassium is more, it is more inside as compared to the outside. Outside potassium is very less, okay, just 3.5 to 5 millimoles per liter, here up to nearly 150 moles, okay. Now because there is more amount of the potassium ions here as compared to the outside, it is from ICF to ECF, so naturally the direction of concentration gradient, that is passive transport, so where the from higher concentration to the lower concentration, so the ion channels will move again in the concentration gradient, that is from higher concentration to the lower concentration. So this is known as concentration gradient, okay, the power that is known as concentration gradient. So potassium ions will diffuse us out. Similarly for the sodium ions, okay, sodium, you know, sodium are more outside or inside? Yes, outside around 150 millimoles per liter, okay. So more sodium will be there, and inside will be just 15 millivolt, okay, 10 times less per liter if we see the concentration. So there will be more sodium ions outside as compared to the inside of the cell, okay. So now if it is permeable, if these are leaky channels, okay, if it is open now, so the sodium will move in which direction? Yes, so your concentration gradient will push this sodium from outside to inside because concentration is more there, okay. Now this cell membrane, these ion channels are not equally functioning. For example, this cell membrane allows the potassium more, even 10 to 100 times more than the sodium channels. So these sodium channels are not so functioning properly, that is it is not permeable to the sodium ions as compared to the potassium. So cell membrane is more permeable to the potassium as compared to the sodium, okay. So selective permeability of this cell membrane, so because of this, so more amount of the positive charge is going outside and only a few amount of the positive charge will be coming inside, though there is a higher concentration of the sodium there, but it is not so permeable. So potassium is more permeable than sodium, so that's why one of the second reason why there is a negativity, because of the selective permeability of the cell membrane. Also this cell membrane is not permeable to proteins and phosphate, these are anions, in negatively charged ions. So these negative charged ions, that is proteins and phosphate, they are not allowed to move outside. So when they are not allowed to move outside, that is this membrane is not permeable to it, more negative charge will remain inside. So more negative charge here and more positive charge is going outside and less positive charge is coming inside. So ultimately the cell membrane, the interior will become negative, okay. So this is one of the reason, that is the selective permeability of the cell membrane, okay, due to the diffusion current. Now third factor to understand this is, we'll go to the mathematical equation Gibbs-Donnan equilibrium, or Gibbs-Donnan equation, or Gibbs-Donnan equilibrium. Now what is this Gibbs-Donnan equilibrium or Gibbs-Donnan equation? So according to this Gibbs-Donnan equation, if we take one beaker or one container and there is some ionized solution, okay, ionized solution means, for example, potassium and chloride ionized solution, that is potassium ions are also there, positive and negative, chloride ions are also present, okay, negative ions are chloride. Okay, positive potassium and negative chloride ions are present. So potassium chloride solution, when this solution is placed across a semi-permeable membrane, that is one semi-permeable membrane is present, and this solution potassium chloride, it is present on either side of this semi-permeable membrane. Okay, so potassium chloride, so according to the Gibbs-Donnan Equilibrium or equation, it is this semi-permeable membrane allows these are diffusible anions and cations. Cations are positively charged, so potassium can diffuse from higher concentration to lower concentration. Similarly, chloride can also go. So at equilibrium, what does it state? It states two things. One is at equilibrium, the concentration or it will be electrically neutral. That means the positive charge, total positive charge, concentration of the potassium, consider this as the side A and this as the side B on either side of the cell membrane. So at equilibrium, the potassium and cations on the A is equal to the chloride anions, that is positive and negative charge will be equal at equilibrium. So similarly, potassium concentration on the B is equal to the concentration of the chloride, that is at equilibrium the solution will be electrically neutral, that is total positive charges is equal to total negative charges. So potassium of A equal to chloride of A, potassium of B is equal to chloride of B. That is the one point. Second point, what does it say is these are diffusible cations and anions, diffusible ions. So for this diffusible ions, the product of cations, that is concentration of the potassium and concentration of chloride, the product of diffusible cations and anions on one side will be equal to the product of the cations and anions on the other side of the cell membrane. So if we consider this example, concentration of the potassium on the side A multiplied by concentration of the chloride on side B will be equal to the concentration of the potassium on the side B and concentration multiplied by concentration of the chloride B. So this is Gibbs-Donnan equilibrium. It says two things. One is at the equilibrium, the solution will be electrically neutral. That means positive charges will be equal to the negative charges. Okay, and the diffusible cations, the product of diffusible cations and anions will be equal to the product of diffusible cations and anions on the other side of the membrane. Okay, hope the concept is now clear. Now considering this equation with respect to human cell, so as you know, in human cell there are certain non-diffusible organic anions. So diffusible ones are the sodium, potassium, chloride. So there will be certain negative proteins and phosphates are also present, which are this for which this cell membrane is impermeable. So consider on this side A there is one more anion, that is like proteins or phosphates. We consider it as X. Okay, so if we consider this and these proteins and phosphates, this will not be present on the other side of the cell membrane. Okay, the same concept if we apply to the human cell membrane, intercellular fluid is one compartment, extracellular fluid is one compartment. This is intracellular fluid, this is extracellular fluid. So in the intracellular fluid, apart from these diffusible anions, there will be non-diffusible this one anions will be present. Now according to this, at equilibrium total charge should be neutral, that is total charge, that is potassium concentration of A should be equal to the all the negative charge, that is chloride of A plus this anion, X anion. Okay, now similarly but here there is no this negative extra negative, so potassium total charge, total positive charges here will be equal to the total negative charge here, chloride of B. So if we consider this, then what does it mean? So what does it mean? If we consider this also, so both this equation, it means that potassium of A is greater than potassium of B. That is, the more concentration of the potassium will be there here as compared to the other side. Potassium of A is greater to potassium of B. Hope you are following these things. Okay. because the total charge should be negative, so we have the total charge should be equal, so the total positive charges will be equal to total negative charges. So this will be like that, and chloride of B will be more than the chloride of A. Okay, so if there is a negative sign here, so here potassium will be more as compared to the other side, and chloride will be more on the other side as compared to the side where there is one more extra anion. Okay, hope it is more clear. Now coming to the next most important equation to understand this resting membrane potential, that is Nernst potential or Nernst equation. Okay, what is Nernst potential or Nernst equation? So within next 5 to 10 minutes we are going to finish it. Please give your kind concentration to understand this very important concept of Nernst equation or Nernst potential. What is this Nernst potential or Nernst equation? So while discussing the selective permeability of the cell membrane, we have already discussed that, see, there are diffusing ion channels, potassium and sodium. Okay, consider this, imagine there is no sodium channel, or sodium channels is not functioning, only potassium channels are functioning. Okay, now because of this concentration gradient, potassium is diffusing from inside to outside, because more potassium is inside as compared to the outside because of this diffusing leaky channels on the cell membrane. Okay, now because of the concentration gradient, potassium is moving from inside to outside, so it is generating some potential, and that potential is known as diffusion potential. That is known as diffusion potential, that is because of this concentration gradient. Okay, that is known as diffusion potential because of this leaky channels. Okay, now this, when this potassium is moving from inside to outside, so it will be creating positivity or negativity inside the cell. Yes, negativity inside the cell, because positive charge is moving outside the cell. Okay, now since potassium is moving outside the cell inside will be becoming negative. So now because of the negative charge here, the cell try to pull the potassium inside because of the electrical gradient. Remember, there are two things, concentration gradient and electrical gradient. Because of the concentration gradient, potassium is going outside and it is creating negativity, electronegativity inside the cell because of loss of positive charges. So now because of the electrical gradient, negativity is increasing here, so potassium will try to go inside this cell because of the negative current here, that is the negativity, that is the electrical gradient. Now a stage will come when the concentration gradient will be equal to the electrical gradient, and there will be no net movement of the ion across the cell membrane. That is, how much potassium is remaining will remain here only, and how much potassium is remaining here, it will remain here only. That stage, it is known as equilibrium potential, and it is given by the Nernst equation. And this equilibrium potential, it is for individual ion. For example, equilibrium potential of potassium. So equilibrium potential of the potassium is given by a formula minus 2.3 RT. Okay, 2.3 RT by ZF, natural logarithm of concentration of potassium inside the cell divided by concentration of the potassium outside the cell. So what does Nernst equation? It shows the relationship of the diffusion potential with the concentration of that ion inside the cell and the outside the cell. That relationship, that is the equilibrium potential. And if we calculate this for potassium, it will be around minus 90 to minus 94 millivolt. Okay, roughly minus 94 millivolt. Okay, that is the Nernst equation. So this is the Nernst equation. So similarly, if we forget this potassium, Okay, consider the potassium ions are not functioning, this ion channels are not functioning, only sodium ion channels are functioning. So sodium will go from outside to inside because concentration gradient will push the sodium ions from outside to inside. Now because of this moving, there will be electronegativity outside as compared to inside because more sodium is going outside. Then because of this negativity, sodium is once again pulled due to the electrical gradient. Again a time will come where the concentration gradient equal to the electrical gradient and there will be no net movement of the ions across the cell membrane, and that will be the equilibrium potential of the sodium. Okay, so it is given by the formula by minus 2.3 RT by ZF logarithm concentration of the sodium outside to the concentration of the sodium inside. Okay, so it will be, if we calculate, it will be plus 61 millivolt. So equilibrium potential of the sodium will be plus 61 millivolt. Remember, equilibrium potential is only for a single ion. Equilibrium potential of potassium is minus 94 millivolt. Equilibrium potential for sodium, it is plus 61 millivolt. Equilibrium potential for the chloride, if we calculate for the chloride channels also, it will be around minus 71 or minus 70 millivolt. Equilibrium potential of calcium, if we calculate, it will be around 132 plus 132 millivolt. Okay, so this is for individual ions. Okay, so because of this Nernst potential also there is a genesis of the resting membrane potential. What we discussed, it was minus 70 millivolt for the nerve cell. So this potassium is one of the most important as it is a more permeable, so it will generate this resting membrane potential. Okay, so if we calculate, it will be minus 94 millivolt. So to simplify this equation, if we put this thing, the values, so it is minus 2.3 actually, minus 2.3 RT. R is the gas constant, T is the absolute temperature, Z is the valency of the ion, here potassium it is 1, and F is the Faraday's constant. Okay, so these are generally the constant thing, and concentration of the potassium inside it will be around 145 millimoles per liter. Outside it will be 3.5 to 5 millimole if you calculate the natural logarithm and all. So if we simplify this formula, we can also write that equilibrium potential for the potassium, if we sum up, these are constants. Okay, this will be variable, concentration of potassium inside and outside will be variable, this will be constant. So if we calculate, so we get formula plus or minus 61 natural logarithm of concentration of the potassium inside to concentration of the potassium outside. Okay, so even this is the Nernst potential, simplified way of the Nernst potential, both are same, you can add even minus 2.3. so if we calculate again, you will get minus 94 millivolt for potassium. Okay, so this is the Nernst potential, which will explain, which will give the value of the diffusion potential, that is, it will give value of equilibrium potential. Equilibrium potential is the potential at which the concentration gradient equal to the electrical gradient of that ion and there is no net movement of the ion across the cell membrane. Hope the concept is clear. It is bit vast, but please try to rewind this video and please once again just revise this thing, the concept will be more clear. Now coming to the final equation to explain this genesis of resting membrane potential, that is Goldman-Hodgkin-Katz equation. Okay, Goldman-Hodgkin-Katz equation. So in the Nernst potential, what we have learnt is it will be showing the electric equilibrium potential of a single ion. Okay, but functionally in a cell membrane, not only potassium, sodium ions will be there, though it is more permeable. Potassium ion channels are more permeable to the sodium, remember. Okay, and chloride channels will be there, calcium, so many will be there. So if we sum up the all the equilibrium potential or the membrane potential, if we consider all the ions together, then that is given by the Goldman-Katz equation. In the Nernst potential, only the individual ion equilibrium potential was given. So if we see the Nernst, if we see the Goldman-Hodgkin-Katz equation, so what does it gives? This is the membrane potential, okay, membrane potential across the cell membrane, that is ultimately this minus 70, how we get through this Goldman-Hodgkin-Katz equation. So membrane potential across the cell membrane, then we have that again constants RT by F, of course Z will be there, that is it will give the RT by F, okay, RT by F, and natural logarithm of, here one more factor, permeability is important. As I said you, potassium is more permeable than sodium, okay, so the permeability of the potassium is multiplied by the concentration of the potassium inside the cell, then plus permeability of the sodium is multiplied by the concentration of the sodium inside the cell, plus permeability of chloride. So for resting membrane potential of a neuron, these three ion channels are more important: sodium, potassium and chloride. So the permeability of the chloride into concentration of the chloride outside the cell, opposite here inside the cell, chloride is outside the cell, divided by permeability of the potassium multiplied by the concentration of the potassium outside the cell, plus permeability of the sodium multiplied by the concentration of the sodium outside the cell. Remember, permeability of the chloride multiplied by the concentration of the chloride inside the cell, okay. Here in the numerator for potassium and sodium it is inside the cell, and in the numerator here chloride concentration is outside the cell, and in the denominator is opposite. Now this equation is Goldman-Hodgkin-Katz equation, and it will finally, if you do this all calculation, R is the gas constant, T is the absolute temperature, F is the Faraday's constant, and this is not natural logarithm of the permeability and concentration of all these ions. Here the movement of these ions depends on the permeability as well as concentration as well as the polarity also. So it will give the minus 70 millivolt. It is sum of all these things, okay, resting membrane potential. So how we got the genesis of the resting membrane potential? So resting membrane potential is the potential difference across the cell membrane at the resting condition of a cell. So at the resting condition of this cell, if a neuron, it is minus 70 millivolt. How we got out of this minus 70 millivolt? Sodium potassium pump will contribute only minimal. Remember, sodium potassium pump will contribute only minus 4 to minus 5 millivolt out of minus 70. Now the equilibrium potential, that is the Nernst equation, for potassium it is minus 94, for sodium it is plus 61, chloride minus 71. If we sum up all this along with the permeability, then the total potential will be negative inside. That is how much negative? Minus 70 millivolt, okay. So this is all about the resting membrane potential. In the next videos we will discuss about the action potential and its properties. Thank you very much.